It's my pleasure to introduce Professor Paul Braun of the Department of Material Science and Engineering at the University of Illinois at Urbana-Champaign. Here today to talk about his research on fast charging, high energy and rechargeable batteries. This is timely considering our recent launch of the low carbon theme at the bp-ICAM, which includes a particular focus on fast charging. At the University of Illinois, Paul is the Ivan Rachev Professor of Material Science and Engineering, as well as the Director of the Illinois Materials Research Laboratory. He's also a member of the bp-ICAM Governance Board, so his research is already well known to us. He began his academic career at Cornell University and received his PhD from Illinois. After a postdoctoral appointment at Lucent Technologies, he joined the faculty of Illinois in 1999, where he has been ever since. Paul was elected a Fellow of the Materials Research Committee in 2018 and is the recipient of numerous awards, including the Illinois Matt S. E. Young Alumnus Award and the Stanley H. Pierce Faculty Award. He has also published research on semiconducting superlattices and self-healing polymers, but today's presentation will focus on his recent work on the electrodeposition of high-performance sodium and lithium-based electrodes for rechargeable batteries. Over to you, Paul.
Great, thank you so much, George. Really my pleasure to talk to the community today. It's quite an honor to see the number of people that have signed in. Look forward to questions you may have. As George said, please put them in the chat box, and I'll do my best to answer them now or at the future. So today I'll talk about ongoing work in my group on fast charging and high energy batteries. Often it's a challenge to have both fast charge and high energy, or high power and high energy, because of the phenomena that tend to counter each other to provide those the underlying physics. So why don't we just start with a little bit of a primer here on batteries, so that good. So I think many of you are quite familiar with this, but if we would look at a conventional lithium-ion battery, and so these are what are called spiral wound. You may hear them as 18650 as a common nomenclature. These batteries consist of alternating layers. The alternating layers consist primarily of an anode layer and a cathode layer. So here's a cathode, here's the anode, and then there's a separator. And so fundamentally, what a battery is storing energy is by moving ions between the reduced state at the anode and the oxidized state at the cathode. And when we look at a battery today, the amount of energy that it can store is proportional to the number of ions and the voltage difference, or the chemical potential difference of the two states. And the charge and discharge rate is proportional to how fast those ions can be moved between the anode and cathode. The rest of the system, which I really won't talk about today, it's quite important, but plays a role in the overall energy and volume density, things like the case, the thickness of the separator, the density and kind of electrolyte that's used, and many other factors. So, if you look at the overall performance of a battery, you really do have to pay attention to many competing factors. But today I'll primarily talk about engineering of the anode and cathode, and a little bit on solid electrolytes. And we'll ignore a number of these other very important factors, such as liquid electrolytes, the thermal effects that may occur, as well as the electrical conductivity of the other components of the systems. But again, if we think about the energy density, this is the volume fraction of the active material and the active material capacity, and the rate performance is simply the kinetics, or how fast ions and electrons can move in these systems. Generally, it's ion kinetics that dominate the rate performance, but there are some special cases where electrical conductivity also plays an important role. Okay, so one question we ask, and almost every important secondary or rechargeable battery today is based on lithium. So while we still see things like nickel metal hydride and nickel cadmium now for more niche applications, the world has largely moved to lithium-ion batteries for virtually all portable electronics and virtually all electrified transportation. I'll briefly mention a little bit about sodium. Sodium, think of it just as a slightly heavier and lower energy version of lithium. It does cost less, and that has some potential advantages. But if we think about a battery is simply moving lithium between being a salt and being lithium metal. For those of you who are chemists, at some point in your career, you may have taken a piece of lithium and put it into water. I would advise doing this wearing very good PPE and a fume hood. And that's because there's a violent reaction. The lithium reacts with the water. It reduces the water as it becomes oxidized, so that lithium is more reducing than water, liberating hydrogen gas. It also liberates an incredible amount of heat, which of course immediately then ignites the hydrogen gas with the surrounding air, yielding to the flames that you see here. However, in its reduced form, lithium salt simply dissolves in water with a very, very small exo or endotherm of solvation, depending on the details of the lithium salt. And so it is really the energy difference of the lithium in these two states that determines the overall energy of the battery. And remember, it's not only the number of lithium atoms or ions, but also the voltage difference. And so it's very important that you have a high voltage battery. And for lithium-ion batteries, the difference in the potential of the lithium is between 4 and 5 volts, depending on the details of the materials you pick. You'll actually see in the literature a large number of reports on people saying things like, high capacity battery or fast charging battery or high power battery. In many cases, those are much lower voltage systems. So while they may store a lot of ions and they may be able to move those ions quickly, if the voltage is lower, the overall energy of the battery is suppressed substantially. So why is lithium interesting? Lithium is interesting because it's small or lightweight and it's highly mobile, and that results in fast kinetics. And it's also interesting because of the difference in the potential between its oxidized and reduced state. Sodium's also be considered. We've had some successes in creating sodium-ion electrodes. Sodium is interesting because it's lower cost, but it is larger and generally lower in voltage. And so it's unclear if sodium will have a real impact on transportation. It may have more of an impact in things like grid scale storage, where one is looking at storing and releasing the energy at much slower rates, and the mass and volume of the system becomes less important. There's certainly emerging efforts on divalent and trivalent ions. People have talked about things like calcium and aluminum, but in these systems, the kinetics is even slower and the voltages are generally slower. So for the most part today, I'll talk about lithium and also mention a few words about sodium. Okay, so the batteries today work quite well. I mean, of course, we would like them to be higher energy density. We'd like them to cost less. But a major challenge is fast charging and high power discharge. And that's something that the lithium alone does not solve. So while lithium can store a rather large amount of energy, if you cannot move those lithium ions quickly between the anode and the cathode, we still cannot charge quickly or provide a high power discharge. And so the rate, of course, is entirely determined by the kinetics of the system. And so I just have a few graphics here and references that you may be interested in referring to. If we think about lithium during charging, so we have lithium ion, it's in an electrolyte. This could be a liquid or a solid electrolyte, but in most cases today, it's in a liquid electrolyte. And so that lithium is highly solvated by the electrolyte. So as you charge the battery, electrons are going to come in and lithium ions are going to come in. So a number of steps might occur. That lithium must be desolvated, and so there is some energy to desolvate as well as the kinetics of that solvation. Until that desolvation occurs, the lithium cannot go into the electrode. Then the lithium has to diffuse into the electrode until it interacts with an electron and reduces. If the lithium is reduced too quickly, it may grow as lithium metal on the surface. If you have a metal anode, which is an area of research, that may not be a problem. However, if it grows too quickly, it probably still grows as a dendrite or grows as a needle. And if that needle comes across and hits the cathode, the battery tends to catch fire. So this lithium ion not only has to be able to desolvate, it has to then be able to diffuse into the anode host, which in most batteries today is a carbon-based host. And only then after it's diffused into the host, then become reduced to the lithium zero state. Now at the cathode, what's occurring is that the lithium is now leaving the cathode. The cathode gives up an electron in this process, and the lithium is solvated. The kinetics of the solvation are quite rapid. They tend not to be rate limiting. But the diffusion of the ions in the electrode certainly can be. During discharge, of course, the reverse is occurring. Now some of the rate limiting steps include desolvation at the cathode, and then some of the same factors of both ion diffusion and electron diffusion. The fundamental difference is that during fast charging, lithium may plate, it may form a dendrite, and that dendrite could short out the cell. Under a high-powered discharge, there's no danger of dendrite occurring. However, you still can have internal heating of the battery. And if there is internal heating of the battery, that locally changes the kinetics. It tends to locally accelerate the kinetics. And that locally accelerated kinetics can still lead to many problems. So there's many ways to model this. You can look at the paper here by another group or a paper from my group. But if you look at these systems, you can break up the anode, the electrolyte, into cathodes into various model spaces and put in parameters that account for diffusion constants, solvation and desolvation kinetics, ion mobility, electron mobility, so on and so forth. And using these models, you can get some idea of what the rate limiting steps are. But what fundamentally appears to be rate limiting during fast charging is the lithium dendrite formation. During discharging, the primary concern is local heating, which then accelerates the transport in that region, which leads to additional heating and feedback that often then leads to failure over time. So what are the factors along with dendrite or some of the kinetic factors? I already mentioned heat generation. That can be both local and global. Lithium dendrites, charging only. You have to pay very close attention to energy density. There are many reports of fast charging and high power batteries. However, many of those have very low overall energy density. So they've put a tremendous amount of porosity into the system. So it speeds up the kinetics. But in doing so, the volumetric energy, or the amount of energy that can be stored inside a box of given size, can be quite low. There's also other factors like cost. There are reports in the literature of being able to reduce lithium dendrite by loading the anode with gold nanoparticles. That might be possible if the gold is present in very low volume fractions, but probably not in practical, realistic volume fractions. Another factor is cycle life. As we know, we want batteries to be able to charge and discharge hundreds or thousands of times. And so while these issues due to heating or dendrite may not show up in the first 10 or 20 or even a few hundred cycles, they may show up over time. And so what one finds is that when batteries are fast charged or high power discharged, they may work fine for a little while, but then over time, the capacity will fade. Another complicating factor is that there's a state of charge dependent behavior. And that's because the electrical and ionic conductivity, as well as the association constants, vary with lithiation and delithiation. So while you may be able to fast charge at 50% charge, you may not be able to fast charge at, say, 10% or 90% charge. And it's important to take that all into account. Okay, so there's a very nice paper that came out about a year ago out of Yi Shui's group, which is really a review on fast charging and the challenges. And the highlighting is mine, but I think the very key challenge is that graphite anodes and transition metal oxide cathodes and liquid electrolytes, the systems that we use today, have fundamental challenges to achieve fast charging without negatively affecting electrochemical performance. What this means is the battery will fail, and safety, meaning the battery will probably catastrophically fail. And so what do I see as really the two key issues? So if we had to elevate and say, what must we solve fundamentally for all of the other factors to then become important? You know, the key issue in fast charging is lithium plating and dendrite formation. So even if we go to a system that contains a metal anode, which is a major goal of the field, if that anode grows too quickly, it will not grow uniformly, but rather lithium dendrites will grow into the electrolyte. And at least up to today, those dendrites have the mechanical properties such that they will eventually crack through the electrolyte, even if it's a solid electrolyte. And the reason is in graphite anodes is because graphite has there's very little driving force for lithium to go into graphite. It's only a few tens of millivolts. And so if you go from a metal anode where we want to plate metal but not grow dendrites, if we go to a conventional graphite anode, if the lithium comes into that anode faster than it can diffuse in and be reduced, it will form a dendrite on the surface. And because the driving force for lithium intercalation into graphite is low, it is very difficult to drive it quickly. If you apply a large overpotential, you get below the lithium zero equilibrium potential, which means metal lithium forms. The second key issue that I see, and related to this, is electrode tortuosity. Conventional cathodes are, say, 50 to 100 microns thick. However, they have tortuosities that may be on the order of 2 to 5. So if you, maybe even a little bit more. So if you have a 100 micron thick electrode with a tortuosity of 5, that means that the average path length for the lithium to get from the top to the bottom is going to be 500 microns. And that exacerbates all of the problems of the kinetics. And so ideally, the cathode would have a tortuosity of 1, meaning that the ions could enter the electrode, and if there are channels, the channels would be perfectly straight. But that's, of course, difficult to engineer in practice. And this applies both on the cathode and the anode. It's a particularly significant problem on the anode because the anode is made of carbon flakes, and the flakes tend to lie flat. And so if you have a flake-like morphology, the tortuosity only becomes worse, which then feeds back into the lithium plating issue. So what are some solutions to this? So I'll mention one here, early work out of our group. It actually has some very fundamental flaws also that I'll mention. And so the early work that we were interested in was how do we provide very effective lithium ion and electron conduction pathways? And so we recognized that one way to provide electron conduction pathways was to create a metal scaffold. And so we determined how to make a stable metal scaffold. We also determined how to put the active material shown in yellow on this. And because this contained a very effective transport pathway for the electrons, the metal in green, and a rather effective pathway for the ions, in this case it was a face-centered cubic structure, so while the tortuosity was not 1, it certainly was not order 5 or 6. And so there was a fast pathway for lithium ions and a fast pathway for electrons. And what we saw is that we could discharge 75% of the capacity in 10 seconds. We could also charge this cathode. So remember, the cathode isn't really where the charging problem is, but we could charge the cathode quite rapidly also. But the problem was that the active material, the energy density, the amount of material in yellow was only about 40% by volume. So while that may have been competitive, 10 or 15 years ago, in today's batteries, the active material makes up something like 70 to 80% of the volume. And if we try to put that much into the system, all of the little holes you see here fill up, and we lose the rate capacity. So on the cathode, this approach has a number of challenges. And we've since moved away from this approach on the cathode, as I'll mention, on the anode, it indeed does have some very important advantages. So the other problem, and the one that we overcame reasonably quickly, was that initially we weren't that good at growing material. So in an intermediate step, we determined how to do electrodeposition of lithium cobalt oxide. And so this is, we use a molten salt. I'll show some of the details on the next few slides. But what we're able to do here is electrochemically grow very high quality lithium cobalt oxide. And so lithium cobalt oxide is sort of the prototypical material. It's one of the first materials used in lithium ion batteries. It's still used extensively An issue is that cobalt is rather expensive, and so in many commercial systems, some of the cobalt has been replaced with other species like nickel or manganese or aluminum, but fundamentally lithium cobalt oxide still remains sort of the centerpiece of many systems. But what we saw is when we used a foam, and this happens to be a thick foam, so it has other things were good about that, we still were limited to sort of 30 to 40%. But what we did see was that now we were getting, and I'll back up one just to show you here. You can see that here it's 4 volts and it's this very slow sloping curve. In a real battery, you want something that has a much flatter plateau, a higher voltage here in the charge state. And so indeed, what we saw is that by using this high quality, we were able to grow high quality material. And at least when we did it in some circumstances, this is a 10C discharge. So this is a 6-minute discharge. We're still getting something like 80 to 85% of the energy out of the system. But I would argue really what that is that's cheating. And it's cheating because the volume fraction of LCO is not high enough. But what we did notice as we did this is that we don't have to make it as a foam. So let's back up and look a little bit at the chemistry here. So this is not your normal electric plating that might be done out of aqueous solutions, that's common for most metals. This is a cathodic process. We're actually oxidizing cobalt oxide. And as the cobalt is oxidized, then it reacts and forms lithium cobalt oxide. And we do this between 200 and 300 degrees C in a molten salt that's a eutectic melt of cobalt oxide, lithium hydroxide, and potassium hydroxide. And the reason for the use of the lithium and potassium hydroxide is not only to control the activity of the hydroxyl groups, but also this eutectic has a much lower melting temperature than pure lithium hydroxide. And of course, cobalt is the precursor for the system. Potassium hydroxide is not consumed, so during plating, you simply add additional cobalt and lithium as needed to maintain the stoichiometry. So I won't go over the details of the Portabay diagram, but simply suffice to say that thermodynamically, there's a voltage and water activity level where lithium cobalt oxide will grow. If the voltage is too high, there's oxygen evolution. If the voltage is too low, one simply doesn't get oxidation to the appropriate oxidation state. And if the water activity is too low, the wrong phase forms. So, these diagrams are not too hard to construct from the thermodynamics, and then one has to go out and experimentally validate it in the laboratory. So if we compare this, conventional cathodes are made between 700 and 1000 C. They're slurries. They're of course not ground by hand, but they're ground up, and then following grinding, they're mixed with carbon and polymeric binders, and they're tape cast on an electrode. Because of that, they contain a number of materials that don't contribute to the energy, namely the carbon and the binder, and they're limited to perhaps 70 to 80% active material. The rest is porosity in these binders. The electrodeposition approach contains no additives, and as I'll show you, it forms robust monolithic electrodes. And what we find very importantly is that it allows us to carefully control the crystallography as well as the internal pore morphology. And that's important because the lithium and the lithium ion and electron transport is very anisotropic. And so by controlling the crystallographic orientation, we're able to orient the material to provide fast kinetics. Okay, so we quickly gave up on using the foams as scaffolds for the cathode, as I had shown you, and we discovered that indeed we could grow these in fairly dense form. This happens to be an aluminum foil, just false colored here, and then lithium cobalt. This is 10 to 15 microns thick. I'll show lots of examples in the subsequent slides. Does it work? Well, this is the cycling. So over 400 cycles, it's lost about 10 to 15% of its capacity. So that's very competitive with today's systems. By X-ray diffraction, it's over 99% pure. I'll show more sophisticated material analysis shortly. Depending on how we grow it, this was intentionally grown to show large crystallites, but one can see that one has large single crystals. These planes here are actually the 003 planes. They do not have fast electron or ion transport. The edges exposed here are 104 and 110 planes. Those planes have open channels or open, those planes are open to lithium ion migration. And also the fast electrical conductivity is along the directions of those planes. And so this crystallographic orientation is important. And I will skip over a lot of the details, but this little bump here is a sign of a high quality material. Oops. Sorry, I hit the wrong button here. If we look at the a little bit more in the details, again, a conventional cathode, say 70% active material plus binder and conductive additives. Here, the active material volume fraction is anywhere from 70 to 95%. It's robust. I mean, this is important for sort of the engineering aspects because the batteries are made by reel-to-reel processes. And this happens to be a 22 micron thick material. And this shows that in a 12-minute charge or discharge, it has about 90% of the energy as the material would at very slow charge and discharge. And if we compare this with a commercial battery, at this sort of rate, it might have 50% of its energy. So there's a very significant advance in the charge and discharge kinetics relative to the slurry-cast systems. Okay, so let's really now zoom in and in a literal and figurative sense and try to understand what's going on. And this is work that we did with Jim Schwo and his group here at Illinois, but using Jim's technique of scanning electron nanobeam diffraction, so scanning over the system and looking at the crystallographic morphology, we saw that the interior of the structure was indeed O3. This is what we had wanted. But that on the surface, there were impurity phases. There was a mixture of O2 and O'3 as well as some other phases. And that's a problem because remember, it's the very surface that the lithium ions have to come into. And if the surface has the wrong crystal structure, it may act as a barrier and inhibit the transport of the ions. Fortunately, we found that if we anneal this in a slightly oxidizing environment at about 400 C, it then this phase grows out. Probably there's some sort of recrystallization from the bulk because this is only on the order of a few tens of nanometers thick. So by annealing, we're able to remove that surface phase. We can see in experiment that once we remove the surface phase, that the both the kinetics and the cycle life improves dramatically. Very much an engineering aspect, but we find that we don't need to use pure cobalt precursor. Most of the impurities simply don't fit in the crystal lattice, and if you use impure precursors, at least a significant number of impurities, they will simply settle to the bottom of the deposition bath and then can be removed at some future point. So somewhat fortuitous, but probably important for a practical application. Okay, so I mentioned a little bit about texturing, and now to give you a little bit of an idea of just why so it's important. So here we're looking at O3 lithium cobalt oxide, the crystal structure, and as you can see, these are the O3 planes, and so the green are the lithium ions. So the lithium ions move very rapidly in this direction, but they move quite slowly in the lateral dimension because they don't make it through the blue layers here very effectively. It also turns out that the electrical conductivity is faster by a few orders of magnitude in this direction. And so if you have a random slurry-cast electrode, the orientation, you can't control the orientation of the grains, but we find that by electrodepositing, we have a lot of control over crystallographic orientation. And in fact, we can grow so the O3 is both normal to the substrate and parallel to the substrate. You don't really want parallel to the substrate, but it helps sort of for understanding the science of the system. But this sort of crystallographic control is really important for fast charge and discharge. So those electrodes I showed so far were a little bit thin relative to sort of commercial systems, and so we were, needed to explore what happens. And so here is, a typical commercial electrode, as I said, is 50 to 100 microns thick. Here's one that is 60 microns thick. This is 87% dense, so this is had about 13% porosity. So this versus say 30% in a commercial system. And even when charged and discharged in the order of 10 to 12 minutes, still releases a significant fraction of the stored energy. And I'll talk more about that quantitatively. Again, a little bit of a practical point, but the surface is quite smooth. That's important because if you're going to use a polymeric separator, if you have a lot of needles coming off the substrate, they'll make a hole through and short it out. We were concerned about that. That the deposition would form dendrites, but indeed we see that is not the case. So a little bit about the properties. The electrical conductivity, this is why this is so important. The electrical conductivity in and out of the O3 plane, it varies by 3 orders of magnitude. So if the O3 planes are oriented like this and you're trying to drive electrons this way, the transport is very limited. Where, of course, when the planes stand up like this, you're going down the fast transport direction. We only have a vague hypothesis at this point about why we can grow certain growth directions. Superficially, one can look at sort of surface and volumetric strain energy, but this is ignoring any of the effects of the solvent the electrodeposition is done in. If you superficially look at the surface energy of the systems, it is favorable to expose the O3, and you'll see these grow in sort of deep crack-like morphologies. So having this orientation probably reduces surface energy, but I don't want to take that too far because the science is just not there at this point. Okay, so let's look at tortuosity. There's some nice papers here. This is one by Vanessa Wood, who has written a lot about using CT to study the structure and tortuosity. And this is more just a generic from some commercial lithium-ion battery company's page. And so you have to remember, again, that the effective diffusion constant is going to be determined very much by the tortuosity. And if this number is large, then you pay a significant penalty. And that's just shown as here is the tortuosity in the anode and the cathode. The anode, which is made of graphite sheets, the in-plane tortuosity or the through-plane tortuosity blows up when the porosity goes below 30 to 40%. And so that really limits the volume fraction of graphite that one can use. And even in something that's a roughly spherical particle, by the time the tortuosity gets, or the porosity gets under 20 to 30%, it also becomes a significant issue. And so, that's one of the advantages of deterministically controlling the electrode structure. So we decided to go and look much more closely at the microstructure of the electrodeposited LCO. What we're looking at here, this is the top surface. You've seen a number of other SEM images of this sort. This is both a lower and higher magnification. Here we are 2 and 12 microns below the surface. You can see these sort of canyon or crack-like structures. These are not thermally induced cracks. They grow in this fashion. And more importantly, if we look at the cross-section, here's a 10 micron distance. And we've taken a number of measurements, but I've just highlighted one here. And so the tortuosity of this electrode is about 1.12, even though it is about 90% or so volume fraction. So, that tortuosity could not be achieved in a slurry. A little bit about rate performance. This is a very thick electrode, so if we want to talk about high rate, this is now a system here that these are different discharge, and one can see that up to about 1 C, so this is a 1 hour discharge, the capacity is pretty good. You might say that's nowhere near commercial. I'll show you sort of commercial benchmarks. But this is twice the capacity and 50% thicker than you would use in sort of any commercial electrode. So this is really a sort of a high energy design, but a high energy design that has much better power performance than you would normally get. And this difference here is the electronic polarization. And so the electronic polarization is near zero. And that compares again with commercial systems where the electronic polarization is also significant. But this is actually, I'd say, more of an apples to apples. What we're looking at here, this is a commercial electrode that has 3.5 milliamp hour per square centimeter and a plated electrode of 3.5. This is C/5, so that's a 5-hour discharge. Now a 30-minute discharge, here's the difference in the energy between commercial and the plated. And then in a 12-minute discharge, the commercial electrode only retains about 25 to 30% of its original capacity, where by creating these low tortuosity structures, one retains on the order of half. The loading is also higher, so one of the reasons this works is because it can be thinner at the same capacity. And so a plated electrode on a given thickness has 30% more energy than a conventional slurry electrode. So I want to make sure we can get to the anode, so I'll just mention briefly, electroplating's fun. You can make a coin cell out of a coin. Don't think there's really practical use of that, but makes for a nice demo. Okay, so let's take 10 minutes here and talk about anodes. So anodes are really, I think, the limit of fast charging, because while cathodes fast charging leads to heating, anodes fast charging leads to catastrophic failures. And so we can handle one and we probably can't handle the other. And so a popular material is now silicon because of its high energy density. It's significantly more than that of carbon, but I'll show you silicon has a much more important advantage than just the energy difference. So a while ago, we also looked at using these sort of three-dimensional structures for silicon, and now unlike the cathode, here the three-dimensional structure is an advantage. The material, as it lithiates, it actually swells and contracts, and so the scaffold enables this open structure, provides a space for the lithium to breathe, and that's quite important. So now in a system, if you take a foil of silicon, it simply fails as it expands, it fragments. If you take a scaffold, on the other hand, because it can breathe in and out, it's able to retain a significant fraction of its capacity. I'll primarily show you work on silicon-grown CVD, but I'll also mention some work on electrochemical-grown CVD, probably more practical for real application. So, one of the things that we needed to think about is how to scale this. So, working with a startup company I've been involved with, they figured out how to scale scaffolds and do some work on electrodeposition. And so this is sort of a 1 meter long scaffold. It's easy to grow these in larger areas. You can just barely see now the metal is the bright white here, and the silicon is shown on the outside. It retains the pore geometry. The tortuosity remains relatively low in this system because it has such an open pore structure. Although, as I mentioned, at the extremes of lithiation, those pores start to close off, and you have to be careful. But the scaffolds can be made in high volume. So let's think about fast charging. So if you take a conventional carbon electrode, that's the one down at the bottom here. And if we take this is all a conventional carbon electrode. If we charge it at a normal rate, say 1 hour, we really don't observe any lithium plating. This is just a coin cell that's been dismantled. On the other hand, if you do fast charging, so this is a 10-minute charge, even after 5 cycles, it looks silvery, and certainly by 50, you can see the lithium dendrite. So what's happening here? Well, graphite only likes lithium by a very small number of millivolts. And so what happens is that you try to push the lithium into graphite, there's simply not much driving force. So another alternative is to go, so here's graphite, it sits at a few tens of millivolts. The other is to go to these titanates. The titanates love lithium. And so you can fast charge this quickly, but because the voltage is so high, you're going to lose 1.5 volts of your cell and the energy drops down. So silicon is a little bit, say, the Goldilocks material from the electrochemical driving force. It sits at, say, 1 to 200 millivolts more positive than graphite. So that gives you a substantial driving force that's on the order of many kT versus a few kT. It also has a much higher volumetric and specific capacity, with the key challenge being these large volume changes that the material overcomes. And so now these are just some electrodes that we either we made or Xerion made. And this is a graphite and a silicon. They have the same loading. The silicon anode doesn't show any lithium dendrite formation. The conventional anode shows considerable lithium dendrite formation. And that's simply because in the conventional anode, we simply couldn't get the lithium in quickly enough, and so it plates on the surface. Here's the voltage you can see. This is the anode voltage versus charge. And so lithium is being inserted into the anode, and so initially at the higher potential, and now it's going through the different silicon lithium phases. And we don't need to worry so much about the cathode voltage, but it's a little bit lower. We lose this sort of 100 millivolts, but that's you can afford that penalty. And so now this is a little bit on fast charging. And so this is now fast charging at 4.5 C. And so there's no lithium plating observed, even though this is being charged now in the order of 12 to 15 minutes. We've done some work up to 6 C, so that's about 10-minute charge. And that's really because fundamentally the lithium likes to be in the silicon. The challenge remains capacity fade. What I'm showing you here is the usual typical best results, which shows 10% fade after 200 cycles. We get that some of the time. Other times we get catastrophic fade. And it's probably due to the swelling and deswelling that leads to mechanical damage within the scaffold. And so, that's a major area of work now in my group, is to try to understand how to mitigate and understand that so that we can reproducibly get a high capacity in the system. To accomplish that, we have some great collaborations. Here's some data taken by my student Nathan Fritz. And it's a collaboration with Professor Pingfang Wang, also at Illinois, and what he's been modeling the strain and mechanics in the system. What we observe is indeed that you see here's the metal. We do indeed observe some delamination effects after cycling, and this is because of this swelling and deswelling. So while we have high capacity, we can get high charge. Mechanics are now becoming, I think, one of the key factors to understand. So I just want to take 5 minutes here to talk briefly about solid-state batteries. There's tremendous interest in solid-state batteries. So far, solid-state batteries have not been very successful for fast charging. And part of the problem is the way that we make solid-state batteries, that we use composite cathodes and either composite or metal anodes that don't work particularly well. And the problem with the composite cathode is you're mixing the cathode with solid electrolyte. The structure has a high tortuosity. The kinetics of diffusion are somewhat limited. The interfacial area is high. There's sort of many problems. And what I would argue is by moving to a dense cathode that's engineered to provide fast ion and electron conduction pathways, this is really how you want to interface with the solid electrolyte. And this is true for both the anode and the cathode of the system. And so here we orient the material, remember, so we get the fast transport directions and the fast electron transport to be normal to the substrate, so it will interface effectively with the solid electrolyte. This limits the area and provides fast growth directions. We're using these halide salts. These are an area of recent interest. They have high voltage stability, and so they're stable. Particularly the indium-based one is stable against lithium cobalt dioxide. There's other variants we're exploring. This is the details of the cell design. Feel free to ask more questions later. As a detail, we use indium because these are not stable at lithium, so there's a current challenge. But these are soft enough that they can be physically pressed to interface with solid electrolyte. So as I mentioned, there are very strong crystallographic effects. If you have it oriented so that the 003 planes are up facing the solid electrolyte, the performance is rather poor. I don't even show the data here on the right because the capacity is too low. And then on the left are just two different kinds of faceting depending on how we grow it. The highly faceted material, which exposes a considerable number of the 101, 104, and 110 planes, has the best performance. Although even the poorly faceted, which is really just this, but with a much higher step density, still has good, but not as good. And if we look at the capacity here, this is in total cathode capacity, the composite cathodes versus the dense cathodes. And what I think is significant is now even at these very high rates, so this is now a 5C, so this is a 12-minute discharge or 12-minute charge. These operate symmetrically. The capacity of the composite or the dense cathode is about twice that of a composite cathode, and this really is fundamentally an effect of exposing the fast diffusing spaces and limiting the tortuosity in the system. Just some sort of high-res electron microscopy so you can see a little bit better. This is the highly faceted material you're looking at. Remember, there were those 003 planes. So here's an 003 terminated facet, and then here is a mix of 110 and 113. The lithium goes in and out of the planes this way, and so when lithium hits an 003, it's largely blocked. In the poorly faceted, it's superficially similar. There's much higher step density, and now the faceting isn't as sharp. This probably leads to more interfacial reactions, but that's just a hypothesis at this point. And these are things that one can control by controlling the chemistry of the system. And one thing I think that, while it's only preliminary, that we're quite excited about is that when we use a highly faceted system, the capacity fade is near zero. It's only a few percent over 100 cycles, where the exact same materials but made up using a composite, so a powder, the capacity is fading much more dramatically. For those of you who aren't really in the battery field, just sort of ignore the data after sort of 80 some cycles here. We've just varied C rates, stepped up, stepped down, and things like that. Another important parameter up here is Coulombic efficiency. You want this number to be high. It is. It's basically 100%, meaning that electrons aren't being consumed in the system. Okay, well, I think I should stop here. I hopefully I've shown you some work on sort of fast charging and high energy on cathodes and anodes, as well as at least a vision for how solid electrolytes might come into play. I start all the bullet points here with electrodeposition because that's really what sort of is fundamentally new and different about the approaches that we're using that really enables the control over the chemistry. Have had great support from many of the U.S. federal agencies and the university. And most important, great colleagues both at Illinois and also at the company. The work that I showed today was primarily of the students shown here, as well as John Cook and Chad Kiggins.